Okay, so I'm going to talk about this calculus applet I found. It's called the area applet. And what it does is it uses approximation methods to find the area under a curve using from basic calculus. So how it works is you type in a function, any function that you want, say sine of x, hit graph. It graphs the function for you. And from here you put in the integral bounds, say minus 2 to 2. A is the lower integral bound, B is the upper integral bound, and then n is the number of geometric objects it uses to approximate the area under the graph. So example, if I put in 5 and I hit fill, you can see, well, it should have used five different rectangles to approximate this area. So if I go up to, say, 20, hit fill, you see as I increase n, I increase the number of rectangles used to approximate this area. As n increases, you can see the area becomes more and more close to the actual area under the graph. And so this is basically how an integral works. It's the limit as n approaches infinity of this kind of Riemann sum, where you split the area into a bunch of different rectangles on your graph, and you take the area of each one, and then you add up all the different areas to get the total area. And so if we make this really big, say 1,000, you can see we're pretty close to the actual area of the graph. And up here, you can use different approximation methods, say left endpoints. What this one does is let me lower m so you can see, it uses a different type of algorithm to create the rectangles than, say, right endpoints. Here's midpoints. So you can kind of play around with this and get a better feel for how Riemann sums and definite integrals work. So it's just a really good way to visualize what's actually happening when you compute an integral. So you're finding the area under this curve by adding up a bunch of these different rectangles. And when you do a different integral, you're taking the limit as this number n goes really high. As you do that, like I said before, it becomes closer and closer to the actual area under the curve.